Okay. Well, thank you all for joining us for today's UCI Center for Machine Learning and Intelligent Systems seminar series. I'm very happy to welcome virtually Ransalu Senanayake. Ransalu got his PhD degree in computer science from the University of Sydney in Australia. Since then, he's moved to Stanford University, where he's a postdoctoral scholar in the Department of Computer Science, working on lots of interesting questions related to decision-making under uncertainty, and how, in particular, how you can do that in ways that are explainable and trustworthy. And he's going to be telling us today about some of this work. So please go ahead, Ransalu.
Yeah, thank you very much, Eric. So today I'm going to talk about propagating uncertainty from modeling into decision-making for trustworthy autonomy. Let's start with an application where we have a full autonomous system. So say we have a self-driving car, it can detect various vehicles and lanes, and then it makes decisions accordingly. However, still we have this kind of accidents. These accidents are everywhere. However, we want to make trustworthy autonomous systems. When I say trustworthy, our systems should be safe, they should be robust, and they should be interpretable. For modeling the environment, we can gather data from cameras, LiDAR or laser sensors, GPS, and then use that model of the environment for decision making. For instance, if blue car is a self-driving car, it can decide to change its lane to left. In particular, I work on uncertainty at the intersection of modeling and decision making. So if we can build models that can provide us some uncertainty bounds, then the decision-making model can look at the various probabilities and decide whether to go straight, change the lane to left or right. So the best decision is always a trade-off because we have to think about both safety and efficiency. In today's talk, I will provide you some examples just to motivate why uncertainty is important, then dig deeper into modeling. How can we model our environment? Then think about how to make decisions and how to develop models that are interpretable. So just think about these scenarios. There's a vehicle in front of us, but we can't really see it. Right? So what are the sources of uncertainty here? When we think about uncertainty, there are two types of uncertainties: aleatoric uncertainty and epistemic uncertainty, or in other words, known unknowns and unknown unknowns. Known unknowns, so the aleatoric uncertainty is the uncertainty inherent to the systems. For instance, so if there's a car in front of us, we might want to estimate the boundary box or the distance to it. But our sensors are never accurate, our models are never accurate. So you have this some noise in the system. That is the aleatoric uncertainty. Unknown unknowns, on the other hand, is the uncertainty that we cannot see. For instance, we see something from behind. Maybe it's a car or maybe it's a truck. If we confuse a truck to a car, that's going to be catastrophic. Just to put it in a one-dimensional form, the noise you can see here is the aleatoric uncertainty, this noise. And in areas where we do not have data is where we have the epistemic uncertainty. Typically, epistemic uncertainty is hard to model, especially in complex environments. It is okay not to know something, but at least we should know what we do not know. And if we do not consider epistemic uncertainty, they could result in crashes. So that's why I work at the intersection of modeling and decision making, and especially look at uncertainty for trustworthy autonomous systems. When I say trustworthy, I look at safety, robustness, and interpretability for high-stake applications such as autonomous driving, planetary exploration, and some healthcare applications. Let's focus on modeling. What you see here is a Mars rover. The objective of this Mars rover is to go around Mars and build a map of its environment. What you see here is a boulder on Mars, and the robot will build a map of elevation. This is the elevation. So in other words, we want to learn a function f that takes inputs as locations, location of the environment, and output the elevation. We are not only interested in the mean elevation, but we are interested in the variance because we want to get the uncertainty. If you look closely, what is behind this boulder is a huge pit. If you look at the mean map, we can see there's a huge pit. We cannot see it. However, if you look at the variance value in that area is really high because we cannot see that area. So that is the epistemic uncertainty. So if the robot does not consider this epistemic uncertainty, it will go here and fall into this huge pit. It would cost billions of dollars for the whole Mars mission. So elevation is one of the quantities that we are interested in modeling, but we have data coming from various sources, various sensors, cameras, LiDAR, GPS, and we are interested in quantifying various things. For instance, what is the elevation, occupancy, speed, direction at location x star at time t star. And we have to use various likelihoods. For elevation or size, we can use a Gaussian likelihood. For occupancy, it could be a Bernoulli likelihood. Occupancy means which areas of the environment are occupied and which areas are free. Okay. Free areas and occupied areas. This information is really important for any robot to move forward because the robot should move in free areas without colliding with any of the obstacles. Then if you think about speed, it could be a Gaussian distribution. We can also have some atypical distribution. For instance, if you want to model the uncertainty of directions, then we can use a von Mises distribution. A von Mises distribution is a probability distribution that goes from minus 180 degrees to plus 180 degrees, but we can think it as a Gaussian distribution wrapped around a cylinder. That is how we measure the uncertainty of directions. Typically, we show it using a polar plot. In most practical applications, our probability distributions should not be unimodal. For instance, if you consider this intersection and if you consider this car, there are various directions the car can go. It could go straight, turn left, turn right. Therefore, we really have to think about multimodality. So our probability distributions should not be really single or unimodal distribution. Okay. So to summarize, I want to model various quantities of the environment. I want to get the uncertainty out of that. So I started using Gaussian processes some time ago. Then really tried to speed up them using stochastic variational inference and other techniques. Then I went to some decision-making folks and I asked them like what they think. Right? So they were like, okay, your model is nice because it can handle uncertainty. They can be updated online. They are kind of interpretable. But the problem is still, whatever the inference technique we used, they were too slow to deploy in a real robot, and they were not memory efficient. And I also had my own challenges. For instance, how can I write down a complex kernel in a Gaussian process? Or how can I handle sparse data points because these point cloud data are very sparse. I also wanted models that work with small data but also scales to large data sets, because when we are gathering data sets from, say, towns, we have a lot of data. Also, sometimes handling non-Gaussian likelihoods is a problem. So in this talk, I am going to firstly introduce a framework called Bayesian Hilbert maps. And for that, I'm going to use this circular building. I'm using this circular building just so that I can explain the concept easily. Okay, so just think this is my circular building, and I have a robot in the middle. This robot has a LiDAR sensor. It has basically a laser sensor that can measure the distance to walls. In this case, robot is at the middle, so the distance is pretty much the same. These red points are where the laser beam hits the wall. Rather than consider the entire laser beam, I get samples along this laser beam. Okay. Now, this is our data set. X means the locations of these points that I selected, both red and blue, laser hits and free points. And Y is free or occupied, 0 or 1. So I collect this data set. Now, if you think about this, we have red and blue, and we want to classify them into two groups. Right. So the separation is circular. It's not a linear separation. However, if we project our data into a high-dimensional space, in that space, data can be separated linearly. So this is very similar to whatever when we use, say, Laplace transforms for solving differential equations. So when we use Fourier transform, it's the same idea, or Koopman operators. So once I have a model, now I can predict anywhere in the environment. So this is the kind of map that I want. I should be able to query anywhere in the environment, because then the robot can query the environment and go to that area. Okay, the circular environment is just for demonstration purposes. We do not have such environments in the real world. Real world environments are like this: complex geometries, complex dynamics. So to deal with that kind of environments, so what we do is we introduce some points. We call these hinge points. I randomly consider these gray points, and I denote them by this tilde, x tilde. X is these blue and white, and x tilde is these gray points. And then I compute a kernel. The kernel is basically a similarity function that takes two inputs and output a real value. If the two inputs are similar, the value is high. If the two inputs are not so similar, then the value is low. For instance, one of the simplest kernels I can use is this squared exponential kernel parameterized by gamma. What we do here is we compute the distance from one of our points, say this xn, to the nearest any of the hinge points, say xm, and compute the distance. So we repeat this for all hinge points. So if we have capital M number of them, we compute this distance, and we compute this feature vector. So this is the feature vector that I'm going to use for classification. So just to explain the same thing in a more deep learning way, so we have this data set, and we want to get this kind of an output. In the first layer, we multiply our inputs with weights, and we have this activation function. Then again, we multiply it by same another set of weights, and we send it to the next activation function. So these kernels are very similar to this activation function, except that we learn the activation functions. To put everything in a very crude way, in a more pictorial, crude way, if you think about a neural network, the first few layers, or the first layer, is trying to automatically extract some features, right? It tries to project data, 2 or 3-dimensional data, into a very high-dimensional space. That is exactly what we are trying to do, but we are trying to learn these activation functions as well. Then do classification. Now the question is, should we go deeper or should we go wider? So how we think about this problem is, if we can extract really rich features in the first layer, classification task becomes very easy. Right? So that's why in the next part of the talk, I'm going to look at how to extract rich features so that classification is much easier. So when I say rich features, there are various ways that we can get these rich features. The method that I explained is one of them. Then we can think about, if we think about like eigenvectors, we can think about Nystrom features or random Fourier features. These cosines, these are more like sinusoidal activation functions. Right. Okay, let me come back to my original formulation. I had this feature vector. Okay. Now, my task is classification. So I have these features and I multiply them with some weights. And because I want to get uncertainty out of this, I introduce probability distributions. I get my likelihood. Likelihood is Bernoulli because I'm interested in whether a given point is occupied or free. That is why it's a Bernoulli likelihood. Then we apply the Bayes theorem. Prior is Gaussian, but likelihood is Bernoulli. Then we can compute the posterior. However, because of the Bernoulli likelihood, the posterior is intractable. Therefore, we have to resort to some kind of an approximate Bayesian inference technique. In this case, we use variational inference, where we try to minimize the KL divergence between the posterior and the approximate posterior distribution. So remember that this weight vector is high dimensional because we have a high dimensional feature vector. It could be 1,000 or 10,000. So I'm not going to explain how we arrive at the exact variational lower bound, but instead I will show you some results, okay, in kind of some complex environment. So we have a robot here and it moves around and we can get this occupancy map. So one means the occupied areas and blue means free areas. These free areas are really important for the robot to navigate. We also get the variance, the third. We can see some areas have a really high variance, the red area. Really high variance means we do not know anything about that environment because the robot cannot see what is behind that point. We can build these aggregated maps and build a map of the environment in pretty much real time for large towns. We also conducted some experiments with, say, real data sets from Waymo. So what I just explained is the Bernoulli likelihood, because we want to look at the occupancy. If we want to quantify something else, say velocity, we can use the same framework, but use a different likelihood. What you see here is some radar data coming from some autonomous vehicles. They have this automotive radar now. We can build these 3D velocity maps. And in the future, we will have these delivery drones. We don't want them to collide with anything else. Therefore, we need to get this uncertainty bounds. And say compared to vanilla Gaussian processes, so sparse Gaussian processes, when we think about these high dimensional features and trying to get uncertainty out of that, the training time is generally much smaller and the query time is much smaller and the accuracy is pretty much the same, if not better. Okay, now let's come back to our previous formulation. I said I introduced weights over the parameters. And I did not talk anything about the kernel. Right? So initially I said I'm going to introduce these gray points or hinge points everywhere in the environment, but how do I really introduce them? Right? Should I randomize them? So probably randomization is not the best technique. What we can instead do is we can introduce probability distributions over the parameters of the kernels. For instance, the locations of the kernel, we have a Gaussian distribution, and say the length scale of the kernel, or that's the hyperparameter. We can introduce a gamma distribution. Then we can write down our Bayes theorem again. Now the problem is, even though we can derive a variational lower bound for the simplest form, when the model gets complicated, deriving a variational lower bound becomes a little bit difficult. Therefore, we resort to probabilistic programming. I really like probabilistic programming because we can define, hey, this is our likelihood and these are our priors. Can you compute us the posterior or the approximate posterior? So when we do this, this is what happens. So this is our data set. Red means 2 obstacles, blue means free areas. And this is the map that we learn over different iterations of this variational inference algorithm. And if you look at kernel shapes and positions, we can see these kernels, they move across the space. And we can also see they change their shape to something like this, because that's where we have the boundary or the wall. Then we can also learn the kernel weights, obviously. So the key here is we can learn any of the parameters using this kind of a probabilistic programming technique. And we learn so many parameters in a very small time. And another takeaway is whether learning is useful. Red is when we learn all the parameters, all the hyperparameters, and blue means when we fix hyperparameters. What we can see is to achieve the same accuracy, we only need very few kernels. So if I translate this into a more neural network form, we don't need to be really wide if we have proper activation functions. Or in other words, if we learn our activation functions, we don't need a really wide network. So that's why it's really important to learn these features properly so that our model is much more simple. And this is another example. We can do this and we can adapt this to various scenarios. Okay, so in the previous case, I used this scared exponential kernel. But what if the scared exponential kernel cannot really capture spatiotemporal patterns? Right? This is especially important when the temporal changes are important. So I'm not going to go through this theorem. What I wanted to show is, this is the famous Wagner's theorem. If we have a probability density function, say this Gaussian, and if we get the Fourier transform of that, we can have a positive definite kernel. Indeed, this is the sufficient and necessary condition. Right? So what we do is we change the form or the way that we write this Wagner's theorem. We write, rather than using the probability density function, we use a quantile. So this is the PDF and this is the CDF. Quantile is just the inverse of that. Okay. So in the quantile, it goes from 0 to 1. And in the y-axis, it goes from -infinity to +infinity. We not just have a typical quantile, but we parameterize this quantile. The parameters of the quantile are theta. If we change the parameters, we get a different quantile. Which means if we learn the parameters this theta, we learn a different kernel. Okay. So just to simplify this equation, rather than having this integral form, we are going to take some samples and approximate it using this dot product. If we get the dot product using some capital M number of samples, we can extract this feature vector. I here is the complex number. And if we simplify it, we can write the same thing in cosines and sines. So if I show this more pictorially, what we are actually doing is we are getting some quasi-Monte Carlo samples between 0 and 1, send it through this quantile for a fixed theta or fixed set of parameters and evaluate them. evaluate the cosines and sine, and use this feature vector for our inference algorithm. So it could be classification or regression. Then we jointly optimize the parameters of our inference algorithm as well as this parameters theta. So we will learn the parameters of our model as well as this kernel parameters theta. With this, actually, we can find really cool kernels, not just squared exponential. We were able to find really weird kernels. And that indeed is useful in some cases. For instance, consider this infilling task. We want to infill this. And if you just use a squared exponential kernel, we really can't infill this because it will not capture this kind of periodic, spatially periodic patterns. And with this, by learning this kind of a quantile, we were able to fill in them, and also we can get the variance. Then we extended this for like predicting into the future for some classical data set. And yeah. So then we extended this work for domain adaptation. For instance, like whenever we get new data, we don't really need to learn everything from scratch, but we can adapt to various domains. We can think about multimodality. And if data is coming from various sources, how can we fuse our models? And how can we predict into the future? Okay, so just to summarize this section, when we have these feature vectors, they are interpretable by construction, and we can estimate uncertainty. They also account for spatial non-stationarity, and we can easily transfer them to new domains. So then I will quickly talk about decision making, how to make uncertainty-aware naturalistic decisions. We have a self-driving car here, and see what it tries to do. It tries to, sorry, the video is not playing. It tries to merge into the left lane. It tries to merge into the left lane, but it fails and it aborts its mission. It turns on its signal, but it was not able to cooperate with other vehicles. Then aborts its mission. But when humans are driving, this doesn't happen very often, right? So in the future, we will have scenarios where human and robot collaborate and cooperate and coexist with each other. Therefore, we really want to model human behavior in order to make decisions. If blue one is a self-driving car, it needs to decide whether it should go straight or change the lane to left. Now the question is whether it should change its lanes and how it should change its lane. What should be the acceleration, for instance? For that, we need to model the behavior of these two red cars. That's what when we are driving, that's what we always do. We try to model other cars and their uncertainty associated with. For that, we want to learn a policy that actually goes from states into actions. State means our environment. Actions could be, in this case, acceleration. So one of the straightforward ways is we can collect trajectory data from data sets, and we can fit a neural network and learn the parameters. For this, we use generative adversarial limitation learning. So, or GALE. GALE is really nice that it can capture really complex nonlinear patterns. But what happens is sometimes it goes wrong, as you can see in this video, and we never know why. I mean, you know, like they collide with each other, and we really can't understand why. So rather than using the black box model, we then looked at this white box model. Okay. So white box model is basically some set of equations someone has developed. Basically, we looked into physics. What people from physics would do, they would develop this model from basic principles. That's really great because if something goes wrong, we know where it goes wrong. But the problem is sometimes it's very conservative. If one of the vehicles just stop, everything else will stop. Because by construction, this model is collision-free. Right? So this model is kind of very conservative. Therefore, what we ended up doing was thinking about this gray box model. We used these kind of equations, add some stochasticity to that, and learn its parameters from data. To explain, I'm not going to explain all the terms, but just to show you the high-level idea, it has some preset coefficients, then it has some coupling variables, and it has some inputs like the current speed, relative speed with respect to the leading vehicle, and the distance. Then it will output the acceleration. What should be my acceleration? So humans have this innate stochasticity when it comes to actions. So rather than considering a single action, we consider this distribution over actions. In this case, actions are accelerations. So to put this into a more modeling form, we have our independent variables and dependent variables, and we want to learn the parameters from data. And this can be actually formulated as this kind of a model where we want to learn the parameters theta of f and g. Right? So you might remember in my previous example, in the mapping scenario, I had a really large vector. That's why I used variational inference, because I wanted to be efficient. Whereas here, I don't have many parameters. Therefore, we use some kind of a sampling technique. In the simplest form, it's particle filtering or sequential Monte Carlo, and we can estimate the distribution of all these theta variables. So we get data for experiments from NGSIM. This is Highway 101 in Ventura Boulevard, I believe, close to Ventura Boulevard. And this is another data set from German highway. What we get data is this trajectory data. And one thing we want to evaluate is my model, is my policy accurate? Another thing is my policy safe? Red is the model that I mentioned. So we look at the accuracy in terms of position error and speed error, and we look at safety in terms of undesirable events. When I say undesirable events, basically whether vehicles collide with each other or if they have some kind of hard brakes. Now, sometimes looking at safety and accuracy is not just enough, because if you want to deploy this in the real world, they should be more naturalistic. If we focus on what happens here, this is when we don't learn. Vehicles collide. This is one scenario. And again, if you focus here, one vehicle just stops and let the other vehicle go. These are at the two ends of the spectrum. In reality, people really don't do this. That's why we need to kind of learn the cooperation. And when we learn this cooperation, you can see they kind of nicely look at each other's acceleration and behavior and then cooperate. So indeed, we did kind of a Turing test-like thing where we showed a pair of videos, and one is real and one is synthetic. Synthetic means driven by our model. And we asked participants, hey, which one is real and which one is synthetic? The responses were pretty much everywhere, which means they cannot really distinguish which is real and which is synthetic. And then we try to deploy this in more high fidelity simulators. When we have this more natural human drivers in high fidelity simulators, we can really do safety validation in simulation rather than testing everything on hardware. So just to summarize this section, we have a human-like gray box stochastic driving policy. We can use them for safety validation in simulation. Finally, let me talk about interpretability. So how to encourage interpretability in complex deep generative models? Interpretability, when it comes to interpretability, there can be various things. One way is say, we have this black box model and how can we explain it? In this talk, what I'm focusing is how to construct a model that is inherently interpretable. Sometimes models are really complex. So for instance, this is a trajectory prediction algorithm, which is really good. It has fully connected network layers, and it has so many LSTM cells, and then it can have a graph neural network. It can be really complex. If we cannot, I mean, obviously we cannot make any complex model interpretable. But if we cannot, then we should at least try to encourage interpretability somewhere wherever it is useful. Let's start this simple variational autoencoder. It takes these images and tries to reconstruct the same image. We have the encoder and the decoder, and we have a latent space. Once it is trained, we can sample from the latent space and generate different numbers. A conditional variational autoencoder is slightly different. In addition to the encoder and decoder, it has this input network. For instance, if we ask it to generate only even numbers, it will only generate even numbers. And for the latent space, typically the latent space is only, most of the time, it's continuous. In most of the applications, I would say, not always. But in this case, we are specifically interested in discrete latent spaces, for instance, Bernoulli distributions or categorical distributions for the latent space, because when we have this discrete latent spaces, it's just a code. It's some numbers. When we have codes, we can think about the interpretability and sparsity. So these discrete latent spaces are widely used in natural language processing, in graph neural networks, and also in some autonomous driving applications here. For instance, in this case, we want to go left, straight, or right, like 3 different decisions. And we want to make the latent space identify those different decisions. Okay, if you look at our conditional variational autoencoder, at the end of each input network, there's this softmax normalization. And softmax is typically not able to produce sparse distributions. Let me provide you one example. So this is how to generate even numbers. We have 10 latent classes, 0, 1, 2, up to 9. And if we use softmax for normalization, the probabilities would be everywhere. However, if we use the normalization function that we developed called evidential softmax, this is what we get. For 0, 2, 4, and so, the probabilities will be close to 0.2. And you can see it's almost uniform distribution for even numbers. So this is the multimodality that we think about when in evidential softmax, or the new softmax equation that we have developed. And we can compare it with other softmax, other sparse normalization techniques. For instance, sparsemax. Sparsemax is really great. It can generate really sparse normalized outputs, but sometimes it just collapses into one mode. Whereas we can see the evidential softmax, it spreads everywhere. And then we apply this to trajectory prediction, so that we can identify different parts of the latent space corresponding to different actions. To summarize this section, we need ways to encourage interpretability in complex deep generative models. And if we use evidential softmax, we can produce sparse multimodal spaces. And generally, I'm interested in this kind of like applications where vehicles interact with vehicles, or like where we have complex interactions, where we have some patients and healthcare providers. Their data is very complex, and we really don't understand. There's so much uncertainty. In this kind of high-stake applications, we really need to look at uncertainty, as well as we really need to understand these models. So in high-stake real-world applications, sometimes just optimizing for accuracy is not the best thing to do. We need to jointly optimize for trustworthy while looking at accuracy. So I would like to give a shout out to all my mentees and colleagues and advisors. Okay, thank you.
Thank you. Let's all give Ransalu a big virtual thanks and applause for a very nice talk. So we have time for questions. You may we're a small enough group. If anyone has one, you can go ahead and unmute and ask. You could also type a question in the chat. So I'll start. I was curious. So when you talked about the kind of gray box model for the autonomous vehicles and coordination, so I understood that you kind of had a sort of a physics-based model in which you were estimating some parameters from data, and then so how did the interaction of vehicles happen? Was that also something that was kind of hand parameterized, or I guess that part seems less obvious how you would parameterize, as opposed to certainly we know some things about the dynamics of an individual vehicle.
Right. Okay. So if you look at the parameters, so how the model is developed, right? So we have this distance to headway, and size of the vehicle could be one thing, and the relative speeds and everything. From that, that actually comes from perception, right? And from that we get some information about what the other vehicle is trying to do. And we also have a parameter called cooperation parameter that I do not show in this model. That's actually how it worked in this scenario. It learns the cooperation using a parameter that is actually a distribution. It's actually a distribution that can capture the stochasticity of different behaviors.
I see.
Yeah. But in general, we could probably we could think about like the trajectory model I showed in the interpretability part. We could also probably incorporate that kind of a more complex model. That was the original plan, but still we haven't done it.
I see. Okay. So you have a sort of parameterized form of cooperation that is in this kind of scenario.
Yeah, in this specific example, yeah.
Okay, great. Are there other questions? Okay, people are shy over Zoom, but nevertheless, thank you for a great talk. Thanks everyone for taking the time to join us. And we will be back next week.